Unit 2, feedback response to questions from students. Requests from students on the following terms: instrumentation amplifiers, isolation amplifiers, operational transconductance amplifiers, OTAs, lock and anti-lock amplifiers, converters, and other op-amp circuits. The first question: a basic instrumentation amplifier has 3 op-amps. That is true, because a basic instrumentation amplifier is an integrated circuit that internally has 3 operation amplifiers and several resistors. The voltage gain is usually set with an external resistor. Question 2. One of the key characteristics of the instrumentation amplifier is its low input impedance. That is false, because the input impedance of instrumentation amplifier is in the order of 10 gigaohm. Question 3. A voltage gain of instrumentation amplifier is set with an external resistor. 100% true. The voltage gain can be adjusted from 2 to 1000 with an external resistor. There is unity gain with no external resistor. A basic isolation amplifier has 2 electrically isolated sections. True. An isolation amplifier is a device that consists of 2 electrically insulated stages. The input stage and the output stage are separate from each other by an insulation barrier. So the signal must be processed in order to be coupled across the insulation barrier. Question number 5. Must insulation amplifier use transistor coupling for insulations? Or most modern insulation amplifier use transformer coupling for insulation? That's false. Some insulation amplifier use optical couplings or transformer couplings to provide insulation between the stages. However, many modern insulation amplifiers use capacitive coupling for insulation. Each stage has separate supply voltages and grounds, so there are no common electrical paths between them. OTN stands for Operational Transistor Amplifier. That is false. OTA stands for Operational Transconductance Amplifiers. Question 7. A lock amplifier has a JFET in the feedback loop. False. Because lock amplifier with a diode, when you place a diode in the feedback loop, lock amplifiers with a BJT, a base emitter junction of a bipolar junction transistor exhibits the same type of logarithmic characteristics as a diode because it's also a PN junction. Question 8. An anti-lock amplifier has a BJT series with the input. That's true. So an anti-lock amplifier is formed by connecting a transistor or a diode as the input element. Question 9. The main purpose of instrumentation amplifier is to amplify common mode voltages. False. A voltage from a pressure sensor is connected to an instrumentation amplifier. It amplifies the same voltage to the drive, a comparator with hysteresis, or a Schmitt trigger. The OTA is a voltage to current amplifier. True. Operational transconductance amplifier, OTA is primarily a voltage to current amplifier, in which output current equals to the gain times the input voltage. Question 11. Linear signal compression scales down all signal levels by the same amount. True. In logarithmic signal compressions, the higher voltages are reduced by a greater percentage than the lower voltages. Thus keep the lower voltage signals from being lost in noise. The OTA has a certain high-low input impedance and a high or low common mode reduction ratio. OTA has a high input impedance and high common mode reduction ratio. Like a conventional op-amp, OTA has two differential input terminals, a high input impedance and a high common mode rejection ratio. Now, let's look to the following circuits. In the first case, I want to refer to the figures above. My question is, which of these circuits is known as an anti-lock amplifier? Circuit D, because an anti-lock amplifier is formed by connecting a transistor or a diode as the input element. Question 14. Which of these circuits is known as a constant current source? Circuit B. Because a constant current source delivers a load current that remains constant when the load resistance changes. V in provides a constant current of I in through the input resistor R in. Since inverting input of op-amp is at virtual ground 0 volt, the value is determined by V in and R in. Which of these circuits is known as isolation amplifier? Circuit C. Because an insulation amplifier is a device that consists of two electrical insulated stages. The input stage and the output stage are separate from each other by insulation barrier, so that the signal must be processed in order to couple across the insulation barrier. Question 16. Which of these circuits is known as instrumentation amplifier? Circuit A. Because an instrumentation amplifier is a differential voltage gain device that amplifies the difference between the voltages existing as in two input terminals. The main purpose of instrumentation amplifier is to amplify small signals that may be riding on large common mode voltages. Op-amp A1 and A2 are non-inverting configurations that provide high input impedance and voltage gain. Op-amp A3 is used as a unity gain differential amplifier with high precision resistor that are equal in value. So in other words, important to know here that R3 is equal to R4 is equal to R5 is equal to R6. Question 17. If you refer to figure A above, and we see R1 is R2 is equal to 30 kilo ohm, and the closed loop gain is 450. The value of external gain resistor RG is equal to, we make use of a formula, RG is equal to 2 times R1 divided by A closed loop minus 1 in brackets. Substitute that values and you will get a value of RG equal to 133.63 ohm. Therefore, the correct answer in this case is going to be number B. Now I refer to figure A above. R1, R2 is 28K. RG is 100 ohm. What would be your closed loop gain of that particular amplifier of what that particular circuit as it's indicated there? A closed loop is 1 plus 2R divided by RG. That's 1 plus 2 multiplied by 28K divided by 100 ohm. So A closed loop is 561. So therefore the correct answer in this case is going to be C. Now we refer to figure B above. If VIN is equal to 5 volts, RIN is equal to 22K, the current through the load RL would be, calculation, Ohm's law, IN is VIN divided by RIN. So that's 5 divided by 22K, 227.72 microamps. We know that IL is equal to IN, that is also equal to 227.72 microamps. So therefore, my correct answer in this case is going to be D. If you refer to figure D above, the VIN is 200 millivolts, RF is 52 kilo ohm, IEBO is 50 nanoamp, then V out would be equal to, first of all, to get the anti-log, you need to take the exponential of a logarithmic anti-log of x is equal to e to the power ln x. Since we know that KT divided by Q is approximately 25 millivolts, you can calculate V out, making use of this formula that negative 180 degrees phase shift RF multiplied by IEDO, and anti-log of V in divided by 25 millivolts. Do your calculations and you will get hold of an answer. V out is equal to negative 7.75. So therefore my correct answer in this case is going to be equal to C. Question 21. Refer to the figures above. Which of this circuit is known as a constant current source? The correct answer is B, because a constant current source is a basic circuit in which a stable voltage source V in provides a constant current I in through the input resistor Ri. Since the inverting negative input of an op-amp is at virtual ground, 0 volts, the value is determined by V in and R in, as I in is equal to V in divided by R in. Which of these circuits is known as a current to voltage converter? Circuit A is a current to voltage converter, because a current to voltage converter converts a variable input current to a proportional output voltage, since practically all of I in is through the feedback path. A voltage drop across RF is I in multiplied by RF. Because the left side of RF virtual ground, 0 volts, the output voltage equal to the voltage across RF, which is proportional to I in. The current applied to a current to voltage converter circuit changes from 4 milliamp to 20 milliamps. If RF is equal to 6 to 5 ohm, what would be the change in the output voltage? In your calculations, you take V out is I in multiplied by RF. First of all, we had to calculate the difference in the current. That's 20 milliamp minus 4 milliamps. That gives you 16 milliamps. So you take 16 milliamps and divide that by 6 to 5 ohm, and that gives you 10 volts. So the correct answer is equal to C. Which of these circuits contains the operational transconductance amplifier? Circuit D contains the operational transconductance amplifier, because the transconductance of an electronic device is a ratio of the output current to the input voltage. Refer to figure B above. If RL is 20K, RI is 1.2 kilo ohm and V in is 2.5 ohm, 2.5 volts. The load current IL would be equal to P, because I in is V in over R in, Ohm's law, 2.5, 1.2K. I in is 2.083 milliamp. IL is equal to I in is 2.083 milliamps. Now I refer to D in the figures above. If GM is equal to 25 millisiemens, RL 25 kilo ohm, what would be the voltage gain? The correct answer is equal to A, because AV is GM multiplied by RL, 25 millisiemens multiplied by 25K, that gives you 6 to 5. This particular filter shown here forms a band stop filter, because the active filter indicated here is a band stop filter, also known as a notch or a band reject or a band elimination filter. You can think of operation as opposite to that of a band pass filter, because frequencies within a certain bandwidth are rejected and frequencies outside the bandwidth are passed. A general response curve for the band stop filter is shown. Notice that the bandwidth is a band of a frequency between 3 decimal points, just as in the case of a band pass filter response. The input signal of an instrumentation amplifier usually comes from an inverting amplifier, a filter, DC power supply, a differential amplifier, or a Wheatstone bridge. Definitely a Wheatstone bridge, because an op-amp comparator used a precision over temperature sensing circuit to determine when temperature reaches certain critical values. The circuit consists of a Wheatstone bridge with an op-amp used to detect when the bridge is balanced. Instrumentation amplifiers are well suited for environments with no signal and no noise, high signal levels that need to be attenuated, no power supply voltages, or small signals superimposed in large common mode voltages. As you can see, the answer is equal to D, but why? Because the main purpose of instrumentation amplifier is to amplify small signals that may be riding on large common mode voltages. An instrumentation amplifier has a high output impedance, high power gain, high common mode reduction ratio, or high supply voltage. In this case, you can see that it's a high common mode reduction ratio. Also, the common mode reduction ratio, CMRR, has a minimum value of 66 decibels. Recall that a higher common mode ratio means better rejection of common mode voltages. An input transducer converts a voltage to current, current to voltage, electrical quantity to non-electrical quantity, and non-electrical quantity to electrical quantity. The correct answer in this case is D. In some respects, insulation amplifier is nothing more than an elaborated op-amp, instrumentation amplifier, rectifier and filter, both A and B. This particular case, it's both A and B. In other words, that an elaborated op-amp or an instrumentation amplifier. The primary function of oscillator in insulation amplifier is to convert DC to high frequency AC, convert DC to a low frequency AC, rectify high frequency AC to DC, produce dual polarity DC voltages for the input to the demodulator. Correct answer is to convert DC to a high frequency AC. The voltage gain of OTA can be calculated using the formula AV is equal to RF divided by RI. AV is GM multiplied by RL. AV within brackets RF divided by RI, close your brackets plus 1. Or AV is equal to 2RF divided by RI. The correct answer obviously is AV is GM multiplied by RL. If an operational transconductance amplifier OTA is used as a non-linear mixer and an audio signal is mixed with an RF signal, the output will be what kind of signal? A square wave, triangular wave, frequency modulated, in other words, a FM signal, amplitude modulated, AM signal. In this particular case, it's going to be an amplitude modulated or an AM signal. If an operational transconductance amplifier OTA is used as a nonlinear mixer and an audio signal is mixed with an RF signal, the output will be what kind of signal? Square wave, triangle, frequency modulated, amplitude modulated, amplitude modulated. When using the OTA in a Smith trigger configuration, the trigger points are controlled by the I out, the I bias, the V out, both A and B above. Both A and B above. In other words, it's controlled by I out as well as I bias. The anti-lock amplifier is formed by connecting a PN junction or a diode or a BJT to the input, to the output, to the feedback loop, or to the inverting and non-inverting inputs to the input. To scale down, large signal voltages without obscuring lower signal voltages should be used. Signal compression, logarithmic signal compressions, natural logarithmic signal compression, anti-logarithmic signal compression. As you can see, the answer is B, because lock and anti-lock amplifier are used in amplifiers that require compression of analog input data, linearization of transducers that have exponential output, and analog multiplications and divisions. And voltage to current converter is used in amplification where it is necessary to have an output load current that is controlled by input voltage, input resistance, output resistance, input frequency. The correct answer is controlled by the input voltage. Question 42. The output of a peak detector is always 70.7% of the input. Is equal to the maximum value of a peak level received since the last reset pulse. Equal to the minimum value of a peak level received since the last reset pulse. None of the above. As you can see, the answer is equal to B. Why? Because the circuit is used to detect the peak of the input voltage and store the peak voltage on a capacitor. Which of the following correctly describe the relationship between bandwidth gain for an instrumentation amplifier? Instrumentation amplifier have no bandwidth since they can only amplify DC. Bandwidth and gain are both zero. Bandwidth increase as gain increases. Bandwidth decrease as gain increases. You can see the answer is equal to D. Why? Because an instrumentation amplifier high input impedance, high common mode reduction ratio, low output offset, and low output impedance. Question 44. Insulation amplifiers can accomplish insulation using a transformer coupling, optical coupling, capacitive coupling, all of above. It is all of the above. Question 45. A voltage gain of the input stage of insulation amplifier is 12. If the output state has a gain of 6, the total voltage gain is equal to, do the calculation here, you see AV total is AV1 multiplied by AV2. It's 12 multiplied by 6, that gives you 72. So the correct answer is equal to C. Question 46. The total voltage gain of the insulation amplifier is 49. If a voltage gain of the input and output stage are equal, the voltage gain for each stage is equal to, let's do the calculation, AV total, AV1 multiplied by AV2. So AV1 is equal to AV2, therefore 49 is equal to 7 times 7. So my correct answer is going to be B. Lock amplifiers are used to compress an anti-lock signal, linearize an exponential output from a transducer, perform analog multiplication and division, all of the above. Why do I say that? Because lock and anti-lock amplifiers are used in applications that require compression and analog input data. Linearization of transducers that have exponential outputs and analog multiplication and division. They are often used in high-frequency communication systems, including fiber optics for processing wide dynamic range signals. Question 48. What is the required value of feedback resistors needed in a current to voltage converter when each 100 microamp of input current needs to results in an output of 1 volt? Do the calculation there, you will find V out is IE multiplied by RF. Manipulate RF, you find V out divided by I in. So RF is equal to 1 divided by 100 microamp. So RF is equal to 10K. So my correct answer, as you can see, is equal to D. Number 49. The current applied to the current to voltage converter circuit changes from 4 milliamp to 20 milliamps. If RF is 625 ohm, what is the change in output voltage? Again, the calculation, V out is I in multiplied by RF. The difference in current is 20 milliamps minus 4 milliamp, that's 60 milliamp. 60 milliamp multiplied by 625, that gives me 10 volts. What is the purpose of a Smith trigger? The OTA uses in the Smith trigger configuration is shown in the figure below. Basically, a Smith trigger is a comparator with hysteresis, where the input voltage is large enough to drive the device into a saturated state. When the input voltage exceeds a certain threshold value or trigger point, the device switches to one of a saturated output stage. When the input falls below another threshold value, the device will switch to its other saturated output stage. Here you can see clearly circuit diagram of the OTA, and as it switches between the input and output at that certain point where positive I bias multiplied by R1, negative I bias multiplied by R1. Now, let's determine the trigger point for the Smith trigger in the circuit below. It's important there, I bias +9 minus -9 minus that 0.7 volts divided by R bias, that is 39 kilo ohm. That gives you 17.3 divided by 39K, that's 444 microamps. So now you can determine the V trigger positive is I bias multiplied by R1. 444 microamps multiplied by 10K, that's 4.44 volts. V trigger negative is I bias multiplied by R1 is negative 444 microamps multiplied by 10K, that is negative 4.44 volts. Question 51, determine the output voltage for the anti-lock amplifier figure. Assume that IEBO is equal to 62 nanoamp. Calculation, V out is negative RF IEBO, the anti-lock are V in divided by 25 millivolts. Do your calculation there and you come to an answer of 4.86 volts. Identify each band filter configuration in the figure. Figure A is a cascade high-pass, low-pass filter. As with a low-pass configuration, first and second order high-pass filters can be cascade to provide 3 or more poles and thereby create faster roll-off rates. Figure A shows 6-pole high-pass filter consisting of 3 Sallen-Key 2-pole stages achieved. B is a multiple feedback. Another type of filter configuration shown in figure B is a multiple feedback bandpass filter. The 2 feedback paths are through R2 and C1. Components R1, C1 provide a low pass response, R2, C2 provide a high pass response. The maximum gain A0 occurs at the center frequency. The Q value of less than 10 are typical in this type of filter. Now figure C, it's a state variable. A state variable or universal active filter is widely used for bandpass applications. As shown in figure C, it consists of a summing amplifier and 2 op-amp integrators, which act as a single low-pass filter that are combined in a cascade arrangement to form a second-order filter. Although used primarily as a bandpass filter, the state variable configuration also provides low-pass and high-pass outputs. The center frequency is set by RC circuits in both integrators. When used as a bandpass filter, the critical frequency of integrators are usually made equal by setting the center frequency of a pass band. Determine the critical frequency in the circuit here below. Critical frequency is 1 divided by 2 pi, the square root of R1, R2, C1, C2. Substitute your values and you get 190 Hertz. The type of active filter shown in this next circuit is a 2-pole low-pass filter. Again, the Sallen-Key is one of the most common configurations for the second-order 2-pole filters, also known as a VCVS, voltage control voltage source filter. A low-pass version of Sallen-Key filter is shown in this particular figure. Specify what you must do to change the gain of the amplifier in the circuit to approximately 20. To change your gain, you change RG to RG is 50,5 kilo ohm divided by AV minus 1. That's 50,5 kilo ohm divided by 20 minus 1. That gives you approximately a value for RG is equal to 2,65 kilo ohm. Determine the output voltage for the lock amplifier in the figure. Assume IEBO is equal to 62 nanoamp. V out approximately equal to negative 0,025 volts. Find the ln of V in divided by IEBO R in. Substitute that values and you get hold of an answer of negative 157 millivolts. Question 58. For the filter in the circuit, in the figure, how would you increase the critical frequency? Typically by decreasing R1 and R2 or C1 and C2. How would you increase again? By increasing R3 or R4. Why? Because an high-pass Salling key configuration is shown in the figure. The components form a two-pole frequency selective circuit. Notice that the position of resistors and capacitors in the frequency selective circuits are opposite to those of a low-pass configuration. As with other filters, the response characteristics can be optimized by proper selection of a feedback resistor and R1 and R2. A single-pole whole-pass filter has a frequency selective circuit with R1 is equal to 2.2K, C 0,0015 microfarad. What is the critical frequency? And can you determine the bandwidth from the available information? You can calculate that. FC is 1 divided by 2 pi RC. Substitute your values, you find the value of 48,2 Hertz. And now, the upper response role due to internal device capacitance is unknown. Therefore, you cannot determine the bandwidth from the available information. Question 60. In the figure below, CA1 is CBE1, 0,047 microfarad, CB2 0,022 microfarad, RA1, RB1, RA2, RB2, and that is all equal to 10K. R1 and R3 is 560 ohm. R2 and R4 is equal to 1K. Determine the center frequency FC1, FC2, 2, and F0, as well as the bandwidth. In the first stage, FC1, 1 divided by 2 pi RC. Substitute your values, you find the value of 338,6 Hertz. The second stage, same formula, 1 divided by 2 pi RC. Substitute your values for the second stage and you find the value of 723.43 Hertz. Now, your resonant frequency F0 is FC1, your critical frequency 1, multiply critical frequency 2, find the square root of both of them. Did that 338,6 Hertz multiplied by 723.43 Hertz, the square root of that, finds an answer of 494.94 Hertz. And the bandwidth is typically 723.43 Hertz minus your 338,6 Hertz, and that gives you 384.83 Hertz. Optimize the state variable filter in the figure below. For Q is 50. What bandwidth if it's achieved is R6 is equal to 10K. Calculation. R5 via manipulation of a formula. So you manipulate the formula Q is equal to R5 divided by 3 multiplied by R6 plus 1 upon 3. We multiply that formula, you find R5 is equal to 3 times R6 times Q minus R6. Substitute that value and you will find that R5 is equal to 1490 kilo ohm. F0, 1 upon 2 pi, FC, so you substitute your values and F0 determine 1,33 kilohertz. Bandwidth is F0 divided by Q, 1.33 kilohertz divided by 50, and that's 26,6 hertz. Optimize the state variable filter in the figure below for Q is equal to 50. What bandwidth is achieved? If R6 is equal to 10K, again, QR5 3 times R6 plus 1 upon 3. Substitute that values. 1490. I think it's exactly the same as the previous one. So it seems to me this one should be a very important question because more than one student asked me that one. F0 is in other words equal to 1,33 kilohertz. Bandwidth F0 divided by Q, that is equal to 26.6 hertz. And that brings us to the end of Unit 2.